Alpha Centauri isn't just one star. It's a triple star system only about 4 light-years away from us, making it the closest stellar system to the solar system and one of the brightest in our night sky. Two of its stars, Alpha Centauri A and Alpha Centauri B, are Sun-like stars orbiting each other, while the third member, Proxima Centauri, is a small, dim red dwarf that orbits much farther out. For decades, astronomers have been staring at this system, hunting for planets that might resemble Earth, but the reality is more complicated and more extreme than most sci-fi stories suggest. This video is part 1 of a larger, Grand Tour series, where we dive deeper into famous star systems outside the solar system and explore their worlds in detail. Before we go further, a quick disclaimer: exoplanet science moves fast. New discoveries can change details about these planets at any time, so if you're watching this months or years after it was made, some specifics may have been updated. That's just how science works. Our picture keeps getting sharper. Proxima Centauri, the violent little neighbor. The first stop on our tour is Proxima Centauri *, the closest star to Earth. Proxima is a dim, cool red dwarf that sits tens of thousands of astronomical units away from Alpha Centauri A and B, the system's center of mass, or barycenter. An astronomical unit, or O, is the distance from the Earth to the Sun, so we're talking about a truly enormous orbit. Because Proxima is so far out, over 12,000 astronomical units at present, it's still debated whether it's truly bound to Alpha Centauri or just passing by in a very long, loose orbit. The evidence right now suggests it is part of the system, and on its roughly 550,000-year orbit it can come as close as about 4,000 astronomical units to the other two stars. But distance isn't the most dramatic thing about Proxima. This star is notoriously violent. It throws off gigantic stellar flares, some comparable to or much stronger than the famous Carrington event eruption from our Sun in the 1800s. A flare so powerful it produced auroras as far south as the Caribbean and disrupted telegraph systems around the world. The Sun produces flares like that on timescales of centuries. Proxima does that kind of thing on timescales of asterisk years. That matters a lot if you're a planet sitting nearby. Proxima d, a super-volcanic, airless world. Let's start with Proxima d*, the innermost of Proxima's known planets. Proxima d is about 1/4 the mass of Earth, roughly 3 times the size of Mars, and it orbits Proxima in just about 5 days. Being that close to a flare star, it's absolutely bombarded by high-energy radiation. If you assume it has no atmosphere, its estimated surface temperature is around 188 degrees Fahrenheit, hot enough to be hostile but not quite molten rock. Think extreme desert, not lava ocean. Because the planet is small, and because flares repeatedly strip away gas from anything resembling an atmosphere, Proxima d probably has little to no atmosphere today. Tidal interactions between the star, Proxima d, and the neighboring planet Proxima b could drive intense internal heating, producing widespread volcanic activity. That would make Proxima d similar in spirit to Jupiter's moon Io, an airless, super-volcanic world, with eruptions continually resurfacing parts of the planet. Not habitable, but spectacularly hostile and scientifically fascinating. Proxima b, the famous habitable zone planet. Next up is Proxima b*, the planet that put Proxima Centauri on every space fan's radar. Proxima b is a roughly Earth-mass planet, with at least about 1.3 times Earth's mass, orbiting Proxima every 11 days. That orbit puts it in the habitable zone *, the region around a star where liquid water could exist on a planet's surface under the right conditions. On paper, that sounds like a dream. The nearest exoplanet in a habitable zone, just 4.2 light-years away. But reality is tougher. Because it orbits so close, Proxima b is almost certainly tidally locked *, showing one side permanently to the star and one side permanently to space, like the Moon does to Earth. Proxima's repeated flares would hammer its atmosphere, stripping it away over time unless the planet has some extraordinary way to replenish it. There are also formation issues. Proxima b may have formed with little water to begin with, and Proxima c's position in the system could make it an efficient delivery system for asteroids and comets that bombard Proxima b, adding to the chaos. Put all of this together, and the most likely picture is not a lush ocean world, but an irradiated desert asterisk. A place that would make Mars or even Venus look relatively gentle. Scientifically, it's a key case study in why habitable zone doesn't always mean habitable planet. Proxima c, a cold giant with possible rings farther out, we reach Proxima c*, the third and currently disputed planet in the Proxima Centauri system. Proxima c is thought to be over 7 times the mass of Earth and orbits at a distance similar to Mars' distance from the Sun, but because Proxima is such a dim star, that places Proxima c in a very cold environment. Its estimated temperature is around -389 degrees Fahrenheit, which strongly suggests an icy composition. With a mass that high and a temperature that low, Proxima c is more likely to be a mini Neptune asterisk, an ice giant with a thick atmosphere and icy interior, than a purely rocky super-Earth. One of the most intriguing hints is that when astronomers tried to directly image Proxima c, it appeared brighter than expected, which could mean it has a large ring system, maybe 5 times the size of Saturn's rings. But there's a catch. That brightness might belong to a completely unrelated background object. So as of now, rings around Proxima c remain unconfirmed. It's still debated whether Proxima c exists at all, but it's been detected via 2 different methods using different telescopes, which makes the case reasonably strong. For now, we'll treat it as a real but not fully confirmed world. A frozen mini Neptune, possibly with a grand ring system. Alpha Centauri A and B. Big stars, few planets. So far, Proxima Centauri has gotten most of the attention because it clearly has planets and it's closest to us. But the Alpha Centauri system also includes Alpha Centauri A and B asterisk, both much larger and brighter than Proxima. Alpha Centauri A is a bit bigger and hotter than the Sun, while Alpha Centauri B is slightly smaller and cooler. Together, they orbit each other with a period of about 80 years, forming a tight binary pair. As of right now, no planets have been confirmed around either A or B. That could change soon. Upcoming and newly launched telescopes are specifically targeting nearby stars, with Alpha Centauri A and B as prime candidates. Within a few years, we may detect multiple planets around them. Currently there is one intriguing candidate, a gas giant orbiting Alpha Centauri A, often called Candidate 1 or Alpha Centauri AB Candidate 1. If it exists, its mass is probably somewhere between Neptune and Saturn, and its orbit appears to place it inside the habitable zone of Alpha Centauri A. Because it's a gas giant, it wouldn't have lakes or oceans on a solid surface, but it could host enormous layers of water clouds, essentially a world wrapped in thick cloud decks. From space, such a planet might look white if those clouds dominate, or take on a more Saturn-like appearance if hazes and other gases color its atmosphere. Could it have habitable moons? In principle, yes. Alpha Centauri A is much calmer than Proxima, so any large moon with an atmosphere would have a better chance of holding onto it. But looking at gas giants in our own solar system, large habitable moons seem to be rare. Most moons around Uranus, Saturn, and even Earth's moon are small, airless worlds of rock and ice. Realistically, if Candidate 1 exists and has moons, they're most likely uninhabitable. But again, uninhabitable doesn't mean uninteresting. Temperate gas giants and ice giants in habitable zones are among the most fascinating planetary environments we can imagine. Why planets around A and B might be rare. One of the reasons planets around Alpha Centauri A and B are hard to predict is the gravitational environment of the system. The two stars are close enough together that their combined gravity could make it difficult for planets to form in stable, close-in orbits. Yet they're also far enough apart that circumbinary planets, worlds orbiting both stars at once, are unlikely to be common or stable very close in. In other words, Alpha Centauri A and B sit in a kind of unlucky configuration, too close for easy planet formation around each star, and not close enough together for circumbinary planets to be a simple solution. That doesn't mean planets are impossible, but it does mean they might be fewer and harder to form than in more typical systems. Today, across the entire Alpha Centauri system, we have *2 confirmed planets, Proxima B and Proxima D, one disputed planet, Proxima C, and one unconfirmed gas giant candidate around Alpha Centauri A. There may be more that our current instruments simply haven't spotted yet. How could we actually explore Alpha Centauri? Given that Alpha Centauri is only a little over 4 light-years away, it's natural to ask, can we send something there? A few serious concepts have been proposed. The most famous is Breakthrough Starshot *, which imagines launching a swarm of thousands of ultra-light, solar-sail spacecraft accelerated to a significant fraction of the speed of light by powerful ground-based lasers. These probes would fly past Proxima Centauri and take close-up images of its planets. The challenges are massive: building and powering the laser systems, keeping the sails stable, protecting tiny probes from dust and damage at relativistic speeds, and transmitting data home across light years. For multiple reasons, engineering, cost, and technology maturity, Breakthrough Starshot is unlikely to happen within the next couple of decades, though the underlying technologies are being studied. A more feasible near-term idea is the * solar gravitational lens concept. In simple terms, this would send a telescope 500 to 1,000 astronomical units away from the Sun, well beyond the orbit of Pluto, to a point where the Sun's gravity can act like a giant lens, bending and focusing the light from a distant target system like Alpha Centauri. If we can line up the Sun, the telescope, and Alpha Centauri perfectly, a solar gravitational lens could produce images of planets with resolutions around 1,000 pixels across, vastly better than the single pixel or 2-pixel detections we're mostly dealing with today. It would still take decades to get such a telescope into position, but unlike Breakthrough Starshot, it doesn't require the same extreme energy budget. As a result, many scientists think a solar gravitational lens might be our best realistic option for getting detailed images of Alpha Centauri's planets within our lifetimes. Alpha Centauri's future, and ours Alpha Centauri, is unique right now because of its * close distance to Earth, which allows more precise measurements and better chances for detailed study. But that won't always be true. Stars orbit the Milky Way and drift through space at several miles per second. Over human lifetimes, that motion is small, but over tens of thousands of years it becomes significant. Alpha Centauri is currently about 4.2 light-years away and slowly moving closer. In roughly 24,000 years, it will reach a minimum distance of about 2.9 light-years from the Sun, briefly making it one of the brightest stars in our sky after Sirius. After that closest approach, the motions of both systems will carry them apart forever. On even longer timescales, billions of years, the Alpha Centauri system will evolve much like our own. Alpha Centauri A will expand into a red giant, likely engulfing any close-in planets, then shrink into a white dwarf. Alpha Centauri B, being slightly smaller, will follow a similar path a bit later. Proxima Centauri, as a tiny red dwarf, will live far longer, trillions of years, before it too becomes a faint white dwarf. Because it's so loosely bound to the main pair, gravitational interactions with passing stars or even black holes could eventually tug Proxima away, ejecting it from the system entirely. Like all star systems, Alpha Centauri is temporary on cosmic timescales. For a brief window, right now, in our era, it's close enough for us to study in detail. That's an opportunity we shouldn't waste. Summary, takeaway, and call to action. So, what have we seen on our grand tour of Alpha Centauri? A violent red dwarf, Proxima Centauri, hosting 2 confirmed planets and 1 likely third, none of which currently look welcoming to life. A possible cold mini Neptune with potential rings, Proxima C, still awaiting confirmation. 2 Sun-like stars, Alpha Centauri A and B, with 1 intriguing gas giant candidate in the habitable zone and the possibility of more planets yet to be discovered. Ambitious exploration ideas, from laser-driven nanoprobes to solar gravitational lens telescopes, that might one day give us true images of these worlds, pixel by pixel. The memorable takeaway is this: Alpha Centauri is close enough to feel like the next door of the galaxy, but still alien enough to challenge every assumption we have about habitable worlds, if we want. To understand our place in the cosmos, studying this system isn't optional, it's essential.
If you enjoyed this video, please like, subscribe to Palsa Lab and turn on notifications so you don't miss our latest uploads. At Palsa Lab, we explore space, science, astronomy, AI, and emerging tech, bringing clear explanations and fascinating discoveries. Have a question or idea? Drop it in the comments. Stay curious, keep exploring, and thanks for watching. See you next time.